Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're looking at examples solving for shear stresses in beams. The next example is a problem from Mechanics of Materials by Timothy Philpott, Wiley 3rd edition. We have a simply supported beam with a uniform load, and the beam cross-section is composed by gluing several wood planks together. This is called a laminated wood beam, and the dimensions are as shown. Some of this is explained in the problem statement. The main thing I want to observe from the problem statement here, the allowable shear strength of the glue is 130 psi. So we'll go ahead and denote that as a given. Tau allowable equals 130 psi. Okay, so we are asked to find, in part A, the maximum uniformly distributed load W that can be applied over the full length of the beam if the beam is simply supported and has a span of L equals 23 feet. Okay, so part A, we find W allowable for those conditions, and since the tau allowable is given in psi, we'll go ahead and take our working units as pounds and inches, so we'll find W allowable in pounds per inch. Part B, we're asked to find the shear stress in the glue at joint H, which is located 4 inches above the bottom of the beam at a distance of x equals 42 inches from the left support. That would be point H right here. It really could be the stress anywhere along that line. And at x equals 42 inches from the end, over here is where point H is. So this is basically asking us to find shear at a specific point in the beam. We'll call it tau sub H, and it's at a location x equals 42 inches and y equals negative 4 inches from the neutral axis. And units here would be psi. In part C, we're asked to find the maximum tension bending stress in the beam when the load of part A is applied. I'll call that sigma max. And in tension, anywhere in the beam, and the units would also be psi. Okay, approach for this problem. Let's focus on part A. We want to find the allowable load in the beam for a maximum shear stress of 130 psi. This is like a design type problem. In order to do this, we need to find the maximum shear stress anywhere in the beam. We need to know the maximum shear force anywhere in the beam. For other parts of the problem, we'll also need to know the maximum moment. So I will quickly sketch a shear and bending moment diagram for this in terms of the applied load W using the symbolic approach. But this is a common case, a frequently occurring case, and we should be able to sketch it very easily. My reactions at each of the simple supports carry half the load, WL over 2, WL over 2 at each support. Shear force diagram, which I'll label as V, jumps up by WL over 2, decreases linearly to negative WL over 2 at the right end. The crosses 0 at the midpoint, WL over 2, WL over 2. Okay, the bending moment is 0 at the ends at the pin supports, increases quadratically to a max in the middle, then decreases back to 0. The peak value is equal to the area of the shear triangle, which is WL squared over 8. So that will be our maximum moment that we'll save for part C. Let's go back to part A. We want to find W allowable in pounds per inch. We note that the maximum shear anywhere occurs at the neutral axis, and for a rectangular section is 3/2 V over A. This is a real nice shortcut to remember for computing the max of a rectangle where you don't have to compute Q. We note that the max shear V is equal to WL over 2. So we'll put those together. Tau max equals 3/4 WL over A. Let's rearrange this a little bit to solve for W. W allowable equals 4/3 A over L times tau allowable. Okay, putting in the numbers, 4/3 times the area of this rectangle, 16 times 6 inches squared. Tau allowable, 130 psi. And the length of the beam, 23 feet times 12 inches per foot. Okay, that computes to about 60.3. And let's look at the units. On the top, inches squared and per square inch cancel out, so we have pounds. On the bottom, we have inches, so this is indeed pounds per inch, which is the units that we are going for. So that's the answer to part A, and we will go ahead and continue this example in the next video.